oh, basically you're doing a PhD thesis on the unit type. And yes, yes, but there are good reasons to do so. And one reason is that, of course, many programs are very fun to write, especially in a nice programming language. But even in those programs, some parts can be a bit boring. And one possible reason for some part of the program to be boring is that it's quite mechanical. You know what you have to do. There is no choice to make. In fact, when there is no choice, you would like the compiler to guess the code for you. So it's a form of code inference. We had a keynote on code synthesis. So indeed, it is a tactic here for a very specific setting, small subpart of programs, and the strategy is to have fun. So in fact, it already exists. We have many examples of this form of code inference. So typically, identifier disambiguation. So which of the different objects with a given name do you mean that can be determined by the type system in various programming language features? Another more general idea are type classes or even implicit. And if you look at proof-assistant tactics, the one with a lot of automation, when you say, okay, guess the proof for me, it should be easy. Of course, the tactic could be, the automation could make many choices for you, but you don't care about which. You only want a proof. Okay, maybe. So in all these cases, there is no real choice to make, and we ask the compiler to guess the code. And I want to go back at a more fundamental question, which is, okay, when is it the case that the code that I'm going to write is uniquely determined by its type? Of course, type classes, for example, are currently not defined in this way as inference of a unique program. My opinion would be that they should be, and in any case, the claim is that understanding this question should help to design these mechanisms. So, more precisely, a type, or rather a pair of a context gamma and a type A, is uniquely inhabited when it is inhabited, and for any t and u of type A, t is equivalent to u. So I need to fix a type system, and in this talk we'll see the simply typed lambda calculus with atoms, product, and sums, and a notion of program equivalence. So what we want is observational equivalence, and in this type system, it is the beta-eta relation that we will define in a few slides. And what we propose is a decision procedure for this question, given a context and a type. Is it uniquely inhabited? Okay, so an example of that, well, the monad instance for the exception parameterized type, if you assume that E is an abstract atomic type on which you don't know anything, is canonical. It is uniquely defined by its type, determined by its type, and each time you've written this instance, you've been ripped off. You should get your money back. The function instance is also canonical, so the map function, but it's not the case of the applicative instance. You have two possible definitions. Okay. So what's the notion of program equivalence that we use to define unicity? So we are in a pure language, simply type lambda calculus. In particular, we have strong normalization, and this is crucial to get a well-defined, decidable equivalence relation. So it is defined beta-eta as a union of two relations, beta, which is reduction, computation, and eta, which gives you extensionality principles. So for function, beta tells you that applying a known function to an argument reduces to the substitution that you expect, and eta tells you that the function t is equal to the function that to x associate t of x. For pairs, beta lets you project out of pairs, and eta tells you that the pair t is equal to the pair first projection of t, second projection of t. And for sums, so here is my syntax for sums, the beta reduction tells you that if you match and you know which side it is, because there is a head constructor, you know which branch to take in the pattern matching. Of course, there is also the case for right, it is identical. And this eta rule tells you that the sum t is equal to matching on t, in the left case returning left, in the right case returning right. In fact, this last rule is what we call the weak eta rule. It's not strong enough. For example, you cannot prove this. That is a valid equality. The pair tu, when t is a sum, is the same as matching on t, and then having the pair left u or right u. And the problem with the weak rule is that t has to appear at the top level, while here it appears under some context, C, which is pair of the whole and U. To get the strong eta rule that allows to prove this equality and all the equalities you want about sums, you just quantify over this context by saying, okay, for any C, C of t is the same as C of left or C of right. Because of this quantification, you guess that this rule is more difficult to handle than the others. And in particular, it was not obvious that this equivalence relation would be decidable. That was proved in 1995. And we didn't know about the problem of unicity. So a natural idea to decide unicity is to have a search process that enumerates normal forms and to stop at 2, saying, no, this is not unique. Okay. We know about proof search, so this enumeration process, we have many ideas and techniques to do that. And we know about equivalence of programs. So what we want here is a proof or type system that characterizes distinct programs in the sense that when you enumerate the valid programs in this type system, you never get duplicates, because otherwise you cannot stop at 2 and say, no, it's not unique. You might have duplicates. Okay. So more precisely, we are looking for a type system for some notion of normal form that is canonical in the sense that if you have two syntactically distinct normal forms, they are inequivalent. They are semantically distinct. Of course, an easy way to get that is to have the type system that rejects all programs. So we also ask it for it to be complete. So each program in the source system should be equivalent to a normal form in this restricted system. And if you have such a system and you know how to do goal-directed proof search on these proofs, you get an algorithm to test unicity. And this idea applies, of course, to any combination of type system and equivalent relation that you may want to think about. And we have such a system for the simply typed lambda calculus with sums. Okay, so first you may have heard of beta short, eta long normal forms. And in fact, because when we say that, we mean weak eta long, it's not such a system. So it does not fit the bill. To see why, let's look at a simple example. You have a function f from x to some subtype y plus y, and an argument x, and you want to find all proofs of x. So of course you can say x. But you can also match on f of x, which is a sum. And in both branches, well, you return x. So this is semantically equivalent to the first program, if you assume purity and strong normalization. But it is a beta normal form. You cannot reduce it. And it is also a weak eta long normal form. And in fact, it's much worse than that, because you can, again, match on f of x in the left range, in the right range. There are infinitely many terms which are beta short, weak eta long normal forms at this time. The problem in the intuition is that you can have equivalent programs that differ syntactically by splitting on terms of a subtype at different places or a different number of times. And we need to quotient over this source of difference. Have a type system that enforces a unique place to cut, to eliminate sums. So natural idea, a good idea, is to say, okay, we will eliminate, we will match on terms of subtype as early as possible in the term. The problem is that this idea, for any subterm of subtype that is used somewhere in your program, you must introduce it as soon as possible. When you are doing goal-directed proof search, the sub-goals you have are holes that are not yet filled. So you don't know which terms of subtypes, will appear in them. And you cannot lift them now for the one that should be introduced now. In terms of type system, it means that it's not a local criterion. So you cannot enforce this maximally early elimination of all useful subterms of sum types. But you can say, okay, let's eliminate all possible sums, the one I will actually use in my proofs, and the one that I will end up not using. And this is the idea of saturation. So a small demo of the algorithm to give you some intuition. On the example I have shown before, so I want to find all possible proofs at this type, and I start by doing saturation. Okay, what are all the terms of sum type that I can compute? So I can try to, the only sum type that I have here is y plus y, and I can indeed get a y plus y by introducing f of x. So I give it a name, and then there is no other way to build this sum type, and there is no other sum type that I can introduce, that I can deduce now in the current context. So saturation stops. And then what I do is, for any variable of sum type in the context, I can, such as z, I can pattern match on it, and I have two subgoals on which, again, I can start saturation. So now I'm looking for all terms of subtypes, but of course, not f of x, which I've already introduced. So I'm looking for new terms to pattern match on. A new term must use the new variable y1. But because y1 is of type y, it cannot be used to build a new term of sum type. So saturation stops without introducing anything, and I'm left to find a proof of x in my context, which is small x. And there is no other choice. Same thing for y2, the second case. So here I have a normal form in my system, but because at each step in the proof I have considered all possible choices, it is the unique normal form. And I've proved that. In general, the algorithm may return either 0 term if the type is not inhabited, 1 if it is uniquely inhabited, like that, or 2 distinct terms at this type, as a constructive proof that it is not uniquely inhabited. More precisely, the algorithm alternates between goal-directed search and saturation phases. And during saturation, the idea is to compute all possible terms of some type and to deconstruct them, but there may be infinitely many of them. Okay, so you need some restrictions on which exactly some terms are you looking for. So first, you don't want to eliminate a term of subtype that you have already introduced in the previous saturation phase. So we have this freshness condition that you should look for new terms that were not typable before in the program. And this is necessary to get canonicity, so to be correct in your answers. You may still have infinitely many choices here. So the first idea is a very old idea of proof search, which is that you don't need to look for any sum types, but just the ones that appear in your context, because you are looking for code-free proofs, morally. And the second idea, which is new, is that, okay, you may have, for example, a function from natural numbers to a sum type. And there are infinitely many neutral subterms at this time. But you only need to keep at most 2 of them, the intuition being that either this sum type is useless to find a proof at your type, and thus the number does not matter, or it is useful to build a program at this type, and then either you have exactly one way to get this sum type, and you have a unique proof, or you have 2 or more, and the answer is not unique. But you don't need to keep a precise count of how many of them you had. These 2 restrictions make the saturation terminate, and also the whole search algorithm. So, to conclude, I haven't had the time to talk about it, but we build upon a beautiful idea of proof theory and the logic programming community, which is focusing. So in 3 seconds at ICFP, focusing is bidirectional typing, but better. And the contribution we have is a type system that is focused and saturating. This is a kind of the new idea, which makes it canonical, and that gives us decidability of the problem of unique inhabitation and ideas on the question of program equivalence. In the paper, we have other examples, such as the one of the monad I've shown, to remark that the simply type lambda calculus is quite a poor type system compared to what we use in practical programming language. But the example that I've shown is an actual useful example in like ML level type system, ML, OCaml or Haskell. So even though we have something very poor, we can already look at some examples, and we hope to extend the system to do more. Extend it to polymorphism and dependent types, because that should be easy, right? So some of you may know that the inhabitation problem is undecidable when you add system F-style polymorphism. And of course, unicity, which is harder than inhabitation, will also become undecidable. But in a sense, that's not a problem, because what we want is to help the programmer with concrete instances. So if we have an algorithm that sometimes say, I don't know, but sometimes give a useful answer, that's already a very good thing. Thank you. Do you have any questions?
That's a very nice talk. So your initial example of the exception monad, it seems to depend really on defining everything very abstractly so that you have an abstract type. Say, I mean, suppose E was string, then there'd be many, many inhabitants.
Yes,
so
of
do you
course.
think this is most useful for very generic programming?
So indeed, what I've said in the first slide is that we hope to look at small bits of useful and non-generic programs where locally you have something that is uniquely guided by the type. But the example that I give here is of a different kind. It's a highly polymorphic library functions. And we hope to have useful application in both cases. But these ones are easier to find. I did the work of looking at existing programs in dependency type languages to find examples of the former kind. Dependency type because you have finite grind type system, you hope to find more of them. And I did some research on some like data mining on like 10 papers on that at the DTP workshop in Boston. So we have some example of this other kind. But indeed, the problem that in practice, ML programs will have in many places defined types make it a bit more difficult. In particular, you may want to think about should I consider a primitive type like int or string to be abstract black boxes so that I get more examples, more useful applications? But then you are not as principled as the technique is, so it's a trade-off to make.
Could you give some intuition for where the number 2 came from?
My intuition is that if you look at unicity, a 2 is the right number, like a non-unique or not unique. In fact, so it's kind of amusing because retrospectively, I would say that this 2 or more property is relatively natural. I think that anyone would believe that this restriction is sensible and sound in terms of having the right answer. But at the time, we were not sure whether it was the case. So if it's not clear to you, that's good because we were not sure either. And in fact, the proof I have is actually parametric. So if you keep at most n neutral terms of each type, you will find more than n different programs if they exist. So it's not just 2. It works for a larger. And one of the guesses when we ask people is some people guessed that it would work for 2 and fail for 3. And in fact, no, it works for any n. That's life.
All right, let's thank Gabriel again.
Thank you.